चोदयेत्रे सूनृतानां चेतन्ति यज्ञं दधे सरस्वती.
Good evening, dear students. Yesterday I happened to meet one of my old timer friend. He asked me, Vishwas, where do you stay in Thane? I said, right in front of Prabhat Talkies. He asked, where is Prabhat Talkies? Well, my answer was right in front of my house. Well, I led my friend from one unknown thing to another unknown thing. I enlightened my friend from something unfamiliar to another thing unfamiliar. Let me tell you, dear students, such a situation should not happen in the teaching learning process throughout the lecture. You and me, we will see to it that we go from something known to us to something unknown, something with which we are very much familiar to something which is unfamiliar to us. So let us start our business. Let me ask you a puzzle, all right? There is a streamlined, uniform flow of water. I take a metal wire and I make a hollow rectangular frame of it. Look at this, something like this. The border of this rectangle is a hollow frame, well defined. I can pass my hand through it. I place it perpendicular to the flow. Now, let us take A to be the area, let L be the length, B be the breadth, and V be the velocity. So, area of that hollow frame defined by some thin metal wire is LB. And the question to ask is, volume of the liquid sweeping through that hollow frame per second. Simple, it's a puzzle. Physics is full of such puzzles. So how much is the volume cutting through or sweeping through that hollow frame per second? Volume of the liquid, I have shown you the flow of the liquid. Well, anybody can suggest me the answer quickly? Okay, it is V into capital A. Simply it is velocity multiplied by area of that frame. Now how we get it? It's very easy. You imagine an identical hollow frame at a distance V behind the given frame. I am showing it in the red color. At a distance V behind. V is the velocity. Now look at the diagram. Essentially, each and every particle lying within this rectangular parallelepiped will travel a distance V in 1 second. So only those particles which are lying in this rectangular parallelepiped will manage to pass through the given area capital A in 1 second. You must have understood that you consider any other particle lying behind the yellow color frame that also will travel a distance V in 1 second but will not manage to cut through or pass through the white color frame, right? So, answer to our question is essentially the volume of the parallelepiped of which area of the base is capital A and the height or the width is V. And what is the volume of such a parallelepiped? Very easy, V into A. Now, let us go from simple to difficult. Let us go from now familiar to something unfamiliar. I will introduce a small complication in the problem. We have seen the area is like this and the liquid is flowing horizontally with a velocity. Now, I like to tilt that area at an angle theta with the vertical. I'll draw the diagram and I seek the answer from you. Just try it. Look at my geometry. This is the flow of water. Definitely, I am asking you puzzles. This is the slant area. To give you the three-dimensional aspect, this is the angle theta made by the area A. Now, my question is the same, but the answer will be different. Let us try to answer this question and you will come to know the unfamiliar situation will be suddenly converted into a familiar situation. What I will do is this. I will complete my diagram as follows. Well, you can see something. Yeah, now you get the three-dimensional view. What I will say now is, this oblique area is made up of two portions. I will do the shading to one portion. Well, look at the portion shown by the white color shading. You will understand that each and every particle which passes through the shaded portion will also pass through the portion through the main area shown at an inclination theta. No other particle which has not passed through the shaded portion will pass through the slant area. Are you convinced about it? Now, do we know how to find the answer for the volume sweeping through the white portion area? Yes, this diagram now becomes identical to this diagram and the answer is V into capital A of the shaded portion. So now I am happy. Yes, VA, can you help me? Cos theta, that's right. So see, the whole game of physics is to go from special case to general case, push yourself from something known to something unknown. Now I'll go one step ahead. All of us know that an area can be denoted by a vector quantity. Okay, this simple rule, this is the given area. It can be denoted by a vector which I have shown by the red color. The rule is that the area vector has to look perpendicular to the given area. The vector is chosen perpendicular to the given area and the length of that vector has to be proportional to the area itself. And now one step ahead we go. Such a term VA cos theta comes so often in physics that we give it a name. We denote it as V bar dot A bar and this symbol is named as dot product or scalar product. That's right. See, it's not that just for the heck of it or sake of it, mathematicians sit together and start defining certain quantities. No, they find that somewhere its application is there. For example, dot product came into existence. It was defined because very often such situation came across in physics. So we have learned this lesson. Now let us introduce more complication into it. And we will handle that. What further we shall do? I consider the flow of liquid. Well, it is a smooth and steady flow, but the flow is like this. And the diagram that I am going to show, or rather I am right now showing you, is called as diagram for velocity lines of flow. This diagram depicts or indicates how the liquid flow will take place. My dear students, you have come across a similar diagram in case of electrostatics. At that time you named it as electric lines of force. In the school physics you have drawn some such diagram, you have named it as magnetic lines of force. Well, the theme is the same. This is the diagram for velocity flow, liquid flow. Alright? And the rule is that wherever the lines are clustered together, they are closely spaced, the velocity in that region is very high. And wherever they are wide apart, the velocity is low. So one complication, my flow has become arbitrary, but it is a steady flow, it is a streamlined flow. Now my frame is not a simple rectangle, but my frame also is arbitrary. I'll show you the frame like this. Well, want to imagine one such? This is an outline. I join it end to end. I see to it that my loop is not coplanar. I don't want a coplanar loop. It's quite arbitrary. Is it non-coplanar? Yeah. And now I hold it. Imagine the liquid is flowing and the velocity is not parallel. It is changing from place to place in magnitude as well as in direction. Fine. The problem has become a little bit complicated. Let us venture into it. Let us try that. Okay, what I shall do is, I know how to tackle this situation. I will consider an element of area. Let me denote it as delta A. Here, that's fine. Delta A. This is the vector representation, delta A vector. And I know at that location how to draw the velocity. Velocity has to be tangential, and well, this will be, there will be some V bar. Let the angle be theta. Let us not look at the entire area and get nervous about it. We need not. I'll ask you a simple question. Tell me what is the volume cutting through or sweeping through this element of area. Let me call it as delta A. Better? Element of area denoted as delta A. Yeah, the answer I think is ready on the blackboard. Correct. Same. But only change that you will make is this. May I know what change you will make? This should be named now as? Thank you, that's right. Any objection? Fine. Now a situation which was unfamiliar to us will become familiar to us. Something very difficult will start looking friendly to us. Have patience and have that insight into the problem. Try to penetrate into the problem. Okay, this is the volume cutting through an element of area shown by the yellow color, but I am interested in the volume sweeping through an arbitrary area marked by an arbitrary outline. What I shall do is, well, I'll do it here. Will it be wise? Summation. Now next question you'll ask me, sir, how to carry out the summation? Don't worry. There are standard ways of tackling it. Symbolically, this is the answer of my question, but let me be honest and tell you, I have manipulation done at two places. Number one, I'll tell you, my element of area that I have chosen is not planar. Basically, it is any arbitrary area. The element of area delta I have shown there could have a curvature, and I know, as per from the mathematics or physics, only a planar element of area can be denoted by a vector quantity. I repeat what manipulation I have done. Number one, my element of area could have a curvature. Look at this nail, or even more arbitrary curvature. Now area vector has to be normal to the element. Now if the element delta A has a curvature, will it have a unique normal direction? No, many. So I have compromised there. Alright. So I am taking the element of area vector at the center of that delta A perpendicular to the central region, and there is a second manipulation that I have done. I will tell you, I have shown you that velocity is changing from place to place. Do you guarantee me that velocity in this region of delta A is the same as velocity in this region of delta A? Not so, not so. I have compromised. I have said that let velocity remain uniform over the extent of delta A, which is a manipulation. So let me tell you, you should have objection to this equality sign. Okay, I'll make it more plausible for you. What this symbol is for? Approximately equal to. Now your faces have calmed down. You will say, okay, LHS is approximately equal to RHS. I am not making tall claims. Okay. Now the next question is, should we be happy with this approximate formula? Is it in vain to search for or try for an accurate formula? Let me tell you, it's Curcy, Isaac Newton, Curcy, Leibniz. One can go ahead and convert this approximate formula into an exact formula. What I shall do is this. Let this element delta A tend to 0, become smaller and smaller, smaller and smaller. We say that delta A becomes infinitesimal. That is infinitely small. And let me remind you at this place one thing. By definition, if delta A tends to 0, delta A cannot be equal to 0. By definition. So delta A becomes smaller and smaller. That's fine. Now, if I allow my delta A to tend to 0, both the manipulations which I have done will be removed. You should have no objection on my formula now. Number one, if delta A tends to 0, will the curvature nature of that element get smoothened out? Will it become more planar, more and more planar? Yes. And I know how to denote it vectorially. So first objection is removed. Secondly, I remember my second manipulation was that velocity will change from place to place. If my delta A tends to 0, can I say that velocity is almost uniform over the extent of delta A because delta is tending to 0? Acceptable to you? So now I will put a symbol. I will say this summation V bar dot delta A bar. Take the limit as delta t tends to 0. This is the summation. Let me now put equality. I have taken the limit as delta t, sorry, not delta t, delta A it is. By this procedure, this is the fundamental concept of limit. If I go to this limit, my approximation becomes equality. Now, this symbol comes so often in physics that we have abbreviated it. This, such a huge symbol is put in a compact manner. Can you tell me what it is that? Pardon? That's fine, perfectly. This is V bar dot dA bar. Look at the change in the symbol. That delta A becomes dA. This is the symbolic representation. I write S here to remind me that this integration is carried over the surface. And now you may ask me, sir, how to carry out this integration? Well, there are standard procedures and methods, but we have learnt a lesson or one important theorem of mathematics via physics. That theorem is integration is the summation taken in some limit. Integration is a limit of summation. This is the very basic theorem of mathematics. I think things are easy now. But we have learnt it via physics. So I repeat, integration is a kind of summation taken in the limit. Well, now let us play more with this. You can have at times the liquid flow like this. How it is set is none of our business. You can imagine such an arbitrary flow of liquid, somewhere the velocity is large, somewhere the velocity is low and all that. In that I wish to place a surface area, but a closed surface area. I will show you the closed surface area, arbitrary. Well, now what do I mean by the word closed surface area? Let me tell you. It is a surface area which has no boundary, which has no boundary. It nowhere begins and nowhere ends. Simplest example, the shell of the egg. The shell of the egg. Peel of the potato. Look at the shell of the egg. Does it have, can you say, sir, this is the starting point and this is the end point? No. This is a continuously running area. So I have given you an example of closed surface area, and such a situation becomes very useful in physics. This is the closed surface area, that's fine. What is the symbol for it? This circle tells me that I am carrying out a surface integral over a closed surface area. Look at this open area, it has a boundary, it has a Seema Resha. You understood? And a closed surface will have no Seema Resha, it is continuous. Well, I will go for this. My LHS remains the same, volume cutting out through this per second. Now, here, let me tell you, there is an inflow of the liquid and there is an outflow of a liquid, inflow and outflow. Somewhere the liquid is rushing, this is an imaginary surface area, it is a complete continuous closed surface area. Somewhere the liquid is entering into this region and somewhere the liquid is leaving this region. And liquid cannot vanish suddenly in between, or liquid cannot generate itself suddenly in between. So I ask you a simple question, something is flowing in per second, something is flowing out per second. What should be the answer of this integral? Somebody said it, that's right, 0. See, suppose somebody said it, what is the answer? That's right, 0. Who taught you? Your brain, your thinking power, you have enormous of it, you make use of it. 0, common sense. What water cannot accumulate inside. Suddenly water is not generated inside. Suddenly water doesn't vanish inside. So simple logic, whatever flows in per second must flow out per second, and the answer is really 0. Let me tell you, this is a special case. The answer of this problem is not always 0. Okay, I'll tell you some trick. This is fine. In this case, the answer is definitely 0. I am happy you got the answer. Who taught you? Did I prompt you? No, you got the answer on your own. You have that ability. Okay, what I will do is this. Suppose there is a source of water, you know, water tap, a very small tap, and water is being oozed out. And the water has some pattern of outflow. Now look at the diagram. Diagram is trying to talk to you. Water is being generated here. Now don't think that water molecules are generated. What I mean, there is a source of water and water is oozing out from it. Now my dear students, tell me, will the answer on the right hand side be 0 or non-zero? Non-zero, because you look at the diagram, everywhere something is flowing out, volume cutting out. There is nothing flowing in. So definitely answer is not equal to 0. Well, now whatever approach, so I have ultimately arrived at a formula. Volume flowing through a given surface per second is given by this formula. This is named as velocity flux. Now, you can replace that velocity vector by any other vector. If you replace that velocity vector by electric field vector, you will call it as, yes, electric flux, so and so forth. I have chosen velocity to be the case. You can replace it by any other vector, and I have got this particular formula. This is called as velocity flux. What you can see here? Filter. चाय बनाना है? बाद में जरूर. So here what I want to depict is, there is a path, there is a boundary. Alright? You are going to answer one very intelligent question. Okay? My question is, what is the volume of liquid cutting through this area per second when the area is like this? What is the answer to this problem? V bar dot dA bar S. Next, I D-shape my area. Can you see I have D-shaped it? In any arbitrary manner, my question to you, what is the volume cutting through this boundary per second? Will it be the same or different? Try it. And my LHS is what? Volume cutting out or sweeping through this area, this area bound by this curvature. This is a circle. Alright, I D-shape it. Again I D-shape it. Will my LHS come out to be different every time, or will remain the same for the given boundary? What do you feel? That's it. It will remain the same. My dear students, my LHS is what? Volume cutting through this particular boundary per second. It has nothing to do with the shape of the area. Alright? So we have learnt one important property of the surface integral. Whatever area you take, do you know, for this particular boundary, do you think there is one and only one, a unique area having that boundary, or you can have any arbitrary area? Any arbitrary area. So the property is, you take any area having the boundary the same, the answer to this particular surface integral will come out to be the same. Are you convinced about it? Because this particular boundary doesn't change. So my LHS is volume cutting through this area per second. That will remain the same whether I take the area this way or of any other arbitrary shape. Now let me tell you, this answer is decided by the boundary, and in physics a number of problems, they come under the category boundary value problems. They come under the category boundary value problems. The answer to the problem is not decided by the actual area, but it is decided by the boundary of that area. Okay, whatever we have done, that is called as integration approach or integral approach to handle the liquid flow. Is that all right? Now, let us do naming ceremony for our lecture. I'll put the title. What do you think? What should be the name? What topic I am dealing with? That's fine. That's fine. Now, we have done naming ceremony. The topic will be surface. That's fine. Integral. I'll add a word, revisited. So we are talking about surface integral revisited, just we are getting acquainted with the concepts and ideas. Whatever approach we have developed, that is called as the integration approach. Now let us look at the same problem. We will handle the liquid flow, right? Our approach will be different. That is called as differential approach. You know, in mathematics, integration and differentiation, these are the two main bodies. Now, and we will see to it that the integration approach and differentiation approach, they concur very nicely, because both the approaches ultimately will talk about the same fact. Let us consider the same flow of liquid. I will construct the coordinate axis. It is x-axis, y-axis and z-axis. There is a flow of liquid. I am not going to draw the flow of the liquid. Imagine the liquid is nicely flowing in a streamlined manner. There is a point P somewhere and I take a rectangular box as shown. The point P is located here and the point P, the velocity of the liquid at point P is given as V equal to, vector V is equal to Vx, it is the x component, it is a function of x, y, z, I cap plus V suffix y, x, y, z, j cap plus V suffix z, x, y, z, k cap. Not a big thing. X component, y component, z component, they themselves are the function of x, y and z, and I, j, k are our standard unit vectors. Alright, I will handle this x component and talk about it. Let this particular width be delta x. This is the point P. Knowing the x component like this, Vx, at the point P, center of that cubical box, I want to know x component at x plus delta x. What is the answer? The answer is given by Taylor series. There is a famous series in mathematics. What is my LHS? I want to know the velocity, x component of the velocity on this face. This total distance is delta x. So what is the distance from the center P up to this face? Delta x upon 2. And I will tackle it as follows. It is x component Vx plus dou Vx by dou x into delta x by 2. This is a standard formula, and plus I get number of terms, but definitely they become smaller and smaller. This is Taylor series. X component of velocity at distance x plus delta x little away from point P is its value at point P plus dou V dou x into delta x upon 2. Now what I will do is let delta x become smaller and smaller. I have talked about. So that my symbol will, this delta x now will become dx. It is going to become smaller and smaller so that really these terms become negligibly small. I will discard those terms. So I have got this. Now what is this symbol? I read it as dou V by dou x. It is called as the partial derivative of Vx with respect to x, means take derivative of this function treating y and z as constant. Now my dear students, partial derivative. You will help me for writing value of the x component at the position x minus dx. Let me show you which position I am marking. Now this is now my dx. I go behind, so will you help me what it is? Vx, yeah, x component, its value at x. Well, I'll put it this way, only Vx for sake of symbol. Vx, x component for, yeah, you have said it, minus dou Vx by dou x into dx by 2. All right. Now liquid flow is there. I am interested in the liquid flow, its component in the x direction. I will do one thing. This is the velocity at this phase. All right. Now this we have chosen to be dx infinitesimal. This is dz This is dy. So that element of volume has a value dx, dy, dz. I'll ask you a question. I know the velocity at this point. It is given by this formula. I have put a flower bracket. The other terms are negligibly small. I multiply here, alright, on this side. I'll take this. I like to do this. Vx plus dou Vx by dou x dx by 2. Alright. And I picked up this RHS and I have multiplied by dy dz. If you look carefully, what is dy dz? The area of the shaded portion. What is this square bracket? The velocity at this face. So tell me, this product, what it denotes? Velocity multiplied by area gives me what? Volume sweeping, that's it. Volume sweeping per second through the x direction. So LHS is volume sweeping through this surface area per second. See, you have answered my LHS. Now, I look at this shaded portion. What is its area? One opposite to it, again dy dz. I take this RHS, I'll put it in the square bracket, Vx minus dou Vx by dou x dx by 2. I'll multiply by dy dz and just tell me what this will represent. Again, volume per second. What I shall say is, maybe from here it is the volume entering per second through this shaded portion, and this term is volume oozing out per second through this shaded portion. Have I gone from familiar to unfamiliar, from known to unknown? I recollect my result. If you want volume sweeping per second, it is not, it has to be velocity into the area. Velocity into the area. In this region, the liquid may be flowing in. I am interested in this shaded portion. Liquid flowing in. And here the liquid flowing out. Influx, outflux. So now I will write the net volume. Net volume in the x direction per second. अरे भाई ये आमदनी है, ये खर्चा है. If you talk of net, what will you write? This minus this. Do it. Somewhere the liquid is coming in per second, somewhere the liquid is oozing out per second. I am using the word net in the x direction per second. I know how to deal with it. This bracket minus this bracket. So what will happen? This also was volume per second. Right? You know, this and this will get cancelled. I am subtracting आमदनी खर्चा. आप समझ गए ना? Your net income. Do you do आमदनी plus खर्चा? ऐसा नहीं करते हैं ना आप. You have to do subtraction. So this will get cancelled with this, and this negative sign will become positive. So what I will get is 2 times dou V dou x, dou V dou x into dx by 2. Will that 2 get cancelled? This term plus this term, so there is a 2 which will get cancelled with these 2. So I will write down, it is dou Vx by dou x. Tell me what more? Dx dy dz. That's it. Thank you, my dear students. And you are going to teach me now what is the net volume. See, the liquid flow could be like this also. Allow me that. You are going to answer my question. I wish to write the LHS net volume in y direction per second. That's it. That's it. Same business I'll do. Do y, and here I'll do. Okay, that will remain the same. Dy, dx, dz. Now, what question I am going to ask you next? You tell me that. What is the net volume sweeping? Net volume sweeping in the z direction. Okay, that's all. Net volume sweeping, net. Per second. And you know the answer, dou V, dou Z, dz, dx, dy. That's fine. All right, now. This is the net. In the x direction, y direction, z direction, my next step will be this. Now, you have talked about the phase dy dz, phase dx dz, phase dx dy, that business. Now, let me talk about how much volume ultimately is flowing out from the entire volume. That is not one phase, all the three pairs of phases put together. Arey bhai, you will add this. So the net volume flowing through the volume element, what do I mean by volume element? It is that shown in the diagram, having the volume dx dy dz per second. I know on the RHS I will do addition, dou V dou x. Tell me, plus. Yeah, I can't hear you. Yeah, plus. Thank you. Bracket dx dy dz. That's fine. I got the net volume flowing through the element. You may wonder, sir, how are you sure flowing out? There may be a circumstance where the net volume is flowing in. Okay, don't worry. You carry out the mathematics. You saw actually, if you carry out that, you will get the proper sign. If you get the negative sign, well, the volume is influx is more. If you get positive sign, efflux is more. You get the appropriate positive or negative sign when you solve a numerical problem. Okay, let me go ahead. This symbol I am going to play with. And you will allow me to do that. Dou x I cap plus dou y j cap plus dou z k cap. Yeah, you are telling me so nice. Have I forgotten this Vx, Vy, Vz? No. I can play like this. I will put a dot here and put, tell me Vx, I cap plus Vy, j cap plus Vz, k cap, and I can't forget dx, dy, dz. Thank you, my dear students. If you know a little bit of dot product, I know I can go back from this step to this step. Check it. Dou x of I cap dot Vx I cap. I cap dot I cap is what? 1. That's fine. So what I get? Dou x of Vx into 1. Should I write that 1? Thank you. One doesn't bother to write that 1. It is understood. Well, now let me tell you, this particular symbol comes so often in physics and mathematics. What is that symbol? Dou x plus dou x I cap plus dou y j cap plus dou z k cap. Yes, it is given a name, del operator. The symbol is del. That's fine. Dot. Thank you. This is called as a divergence of velocity vector. The name is divergence of velocity vector. The symbol is del dot. Del dot. Fine. Now, don't forget what is my LHS. It is the volume, overall volume sweeping out per second through the given volume element. Now, let us venture into next step. I have got a closed surface area like this shown by the yellow color. I have told you how to write the formula for the net flow, volume flowing through the volume element per second. Now I say I am interested in the closed surface area bound by the yellow boundary of which element dx dy dz volume element is a part. I want total flow, total volume flow through closed surface S per second, surface S per second is equal to, अरे भाई, this is the volume oozing out through the element dx dy dz. तो आप बताओ मुझे पूरा का पूरा चाहिए. What you will put on the RHS? That's it, integral. Of what? Divergence of v dx and here this is dv. Dx dy dz, I am cautious, I put d vol, means it is the element of volume. Least I should confuse between v as the velocity and v as the volume. That's fine. So this is volume integral. My dear students, what this formula denotes? Same thing. Do you remember our earlier discussions? This formula tells me it is the volume sweeping out through a closed surface area. I am here in this diagram, I am again talking of the same thing. LHS is what? Volume sweeping out through the closed surface area. So this LHS is equal to this LHS. Should I convince you about that? LHS is same. So what RHS must do? Be same. So I write down RHS has to be the same, that is divergence of V bar volume element. I know it is d of capital V and this may be small v. This the volume integral has to be equated with V bar dot dA bar and here closed surface S. My dear students, starting with the puzzle, you recollect, I started with this puzzle. You answered this puzzle, then you answered this puzzle, then half the questions were answered by you. So who taught you? Me? You taught yourself. I was the catalyst. Most of the things I used to ask, what is LHS, what is RHS, and I got the answers from you. And my dear students, let me tell you, what we have stumbled upon is the famous theorem from physics and mathematics called as divergence theorem. One way is that what is oozing out from the closed surface per second must be what is generated or what is created per unit volume, capital V enclosed by the given surface S. Divergence theorem. Okay. Vastly enjoyed being with you. Thank you very much.